This is a podcast of the Nuffield Department of Medicine. Today we've asked Professor Dave Stewart to talk to us about structural biology and vaccines. Hi, Dave. What is structural biology?
I guess if you want to understand biology, think about how you'd want to understand how a car works or anything around us that's rather complicated. What you need to do is to understand the individual pieces, how they fit together, and how the machinery of the system works. So structural biology is trying to do that in a very detailed way for organisms like us. To do that, you need to go into terribly fine detail because we're made up of millions of cells, and each of those has incredibly intricate machinery within it, which operates at a molecular level. So structural biology is trying to understand how those nanomachines work and how they affect the sort of all the complexity that is life and allows us to sort of operate as we do.
How can structural biology help us improve vaccines?
Structural biology is, in principle, a great way to try and improve vaccines because the way vaccines work is a very physical process. The basis of a vaccine being effective is that the virus or bacteria that the vaccine is to control is physically recognized by molecules that are produced in your body. Those molecules recognize, attach to, and neutralize, and then lead to the elimination of the virus or bacteria. So it's a very simple, in principle, physical process of recognition. So if we understand the structure, we can see the chemical basis of that recognition, and in principle we can try and redesign or design a mimic of the pathogen that might elicit a better response from us, a more effective response to the actual virus or bacteria. And we can do that by making a mimic that is stronger, has better physical properties, or it might be that something about the structure leads to antibodies that we produce which are going to neutralize not just that exact pathogen but closely related pathogens. So we might be able to, by clever design, produce a vaccine that can give slightly broader protection than you generally get with a very specific virus or bacteria.
Can you give us an example of this kind of work?
I'll give you an early example from some work that we're doing. At the moment, for many years, the World Health Organization has had a program to try and eradicate poliovirus from the globe. And that, for quite a long time, has gone pretty well. So there are now really rather few countries where people get polio. And that's because there's been mass vaccination. However, it's going to be difficult to completely stop vaccinating. And one reason for this is that we immunize people with vaccines that include attenuated viruses. A consequence of that is within the population there are individuals that, even though they've been vaccinated, actually have poliovirus replicating in them and they shed the virus. So if we stopped vaccinating, then there'd be a potential for the virus to completely explode into an unvaccinated population. So what we're looking at is to try and understand the structure of the poliovirus and make a synthetic version of it that will be safe because it won't have the viral genome. It couldn't divide. It's not a virus. It's just essentially a synthetic copy. If we could replace the vaccine with such a synthetic vaccine, then there'd be no chance of the virus replicating in people that have been vaccinated. So it would be quite a useful tool in the end game of trying to sort of move to a world where not only have we eliminated polio as a disease, but we've eliminated it as a virus and as a potential threat, and then one could imagine eventually stopping vaccination altogether.
What are some of the most important lines of research that have developed in the last 5 to 10 years in this field?
Depends how broadly you cast the net as to the research. I mean, I'd like to sort of step back a little bit from just the vaccine side, but to try and say how do we understand the interaction between, say, viruses and their hosts. And the last few years have seen some really sort of interesting developments, particularly in the way we can image living systems. So there's been wonderful developments in light microscopy so that we can track viruses as they interact with cells, living cells. And also the developments in microscopy with electrons. Electron microscopy is now a fantastically powerful technique that can give us the sort of atomic detailed information that we need to be able to look at these pathogens and try and design better therapies against them.
Why does this line of research matter? Why should we invest funding in it?
Well, I hope that it will make a difference in terms of people's health and in terms of animal health in the long run. But it's very important to realize that most of the science that people do doesn't lead to an immediate new drug or anything like that. If you look at where the new therapies come from, they usually come from things that people started working on maybe 25 years earlier. So there's a very long, slow burn before you get a result. And I think it's very important to realize that you do the fundamental research, and it may be for you or for others later to really make the translational impact. But it will be there eventually, and we see it as new therapies come through. But at the time you're doing the first research, you can't necessarily predict exactly how it'll turn out and how it will impact on human health.
How does your research fit into translational medicine in the department?
Well, I try to indicate that it fits in some ways, but in other ways there's a lot of basic elements to it that are a bit separate. So we're not there at people's sort of bedsides with these things. There's quite a gap, and what we the people we tend to work most closely with are the companies that are going to be developing new vaccines and things like that. However, it's also important to have within the university the ability to do the clinical trials and the ability to test vaccines and things like that, which is one of the strengths of Oxford. So it's a complicated fit. There's a lot of things that we do that don't immediately translate. Some things do.
Thank you.